In this presentation, I would like to tell you about how we, at ScyllaDB, implemented per-partition rate limiting, an overload protection feature designed to mitigate negative effects of some pathologies in the workloads. The talk will explain the problem this feature addresses and how the feature works. Furthermore, I will tell about the performance issues related to error reporting in ScyllaDB that we uncovered during development and how we addressed them. My name is Piotr Dulikowski. I am a senior developer at ScyllaDB. Let's start with a quick recap on ScyllaDB's architecture. ScyllaDB is a distributed database. A single cluster is composed of multiple nodes, and each node is responsible for storing and handling a subset of the total dataset. Furthermore, each node is divided into shards. A single shard is basically a CPU core with a chunk of RAM assigned to it. Each shard of the node handles a subset of the data the node is responsible for, which means that the CPU cores rarely have to communicate with each other, minimizing the cross-core synchronization cost. All of this makes ScyllaDB not only horizontally scalable, but vertically scalable as well. The most granular unit of partitioning is called, a partition. A partition in a table is a set of all rows which share the same partition key. For each partition, a set of replica nodes is chosen. Each of the replicas is responsible for storing a copy of the partition. While read and write requests can be handled by non-replica nodes too, the coordinator needs to contact the replicas in order to execute the operation. Replicas are equally in importance and, depending on the consistency requirements of the user, not all have to be available in order to handle the operation. This data partitioning scheme works well when the data and load are evenly distributed across all partitions in the cluster. However, a problem can occur when one partition suddenly starts receiving a disproportionate amount of traffic compared to other partitions. Because ScyllaDB assigns only a part of its computing resources for each partition, the shards on replicas responsible for that partition can easily become overloaded. The architecture doesn't really allow other shards or nodes to come to the rescue. Therefore, even a powerful cluster will struggle to serve requests to that partition. We call this situation a hot partition problem. What's more is that the negative effects aren't restricted to a single partition. Each shard is responsible for handling many partitions, so if one of them becomes hot, then the partitions which shared at least a single replica shard will be affected too. Sometimes, hot partitions may appear because the cluster's schema does not fit your data. You need to be aware of how your data is distributed and how it is accessed and used. Then model it appropriately so that it fits ScyllaDB's strengths and avoids its weaknesses. Unfortunately, the responsibility lies with the system designer. ScyllaDB won't repartition the data automatically for you. While it makes sense to optimize your data layout for the common case, however, the uncommon case will inevitably happen. For example, your users will not always behave as expected. It's very important that their behavior do not bring the whole system to a grinding halt. What's more, the source of the problem may not only originate from outside of your system, but also from the inside. No matter how well we test our code, bugs do happen and may cause some parts of the system go crazy, leading to highly unbalanced workloads. Therefore, it's not only important to think about the overload protection at the system level, but at the per-component level as well. The core of the issue of hot partitions is that requests are incoming with a greater rate than the replica shards are able to process them. The requests form a queue which keeps growing. As the queue grows, requests need to wait longer and longer, ultimately reaching a point where most of them fail due to them timing out before they even start being processed. The system has good throughput because it accepts a lot of work, but poor goodput, as most of the work will ultimately be wasted. The problem can be mitigated by rejecting some of the requests when we have reasons to believe that we won't be able to process all of them. Requests should be rejected as early as possible and as cheaply as possible in order to leave the most computing resources for the remaining requests. While it is not always possible to correctly estimate the impact a single query will have on the replicas, we can apply some heuristics to decide whether we will be able to handle it. Let's say that we don't expect more than X writes per second to any particular partition. In ScyllaDB 5.1, we implemented per-partition rate limiting, which follows that idea. For a given table, you are able to specify a per-partition rate limit, separately for reads and writes. if the cluster detects that reads or writes for a given partition start exceeding user-defined limit, it will start rejecting some of the requests in an attempt to keep the rate of unrejected requests below the limit. While the feature tries to accurately apply the defined limit, due to the distributed nature of ScyllaDB, the actual rate of accepted requests may be higher. Keep in mind that this feature is not meant for enforcing strict limits, for example for API purposes, but was rather designed as an overload protection mechanism. The inaccuracies are there due to the details of the implementation and will be explained in the next sections. So now I will explain how this feature works. In order to know how many requests to reject, we need to estimate the request rate for each partition. Because partitions are replicated in multiple nodes, and not all replicas are usually required to perform an operation, there is no obvious single place to track the rate. Instead, we perform measurements on each replica separately and use them to estimate the rate. Let's zoom in on a single replica and see what is actually being measured. Each shard keeps a map of integer counters indexed by token, table and operation type. When a partition is accessed, the counter relevant to the operation is increased by 1. On the other hand, every second we cut every counter in half, rounding towards 0. Due to this, it is a simple mathematical exercise to show that if a partition has a steady rate of requests, then the counter value will eventually oscillate between x and 2 times x, where x is the rate of requests per second. We managed to implement the counter map as a hash map that uses a fixed, statically allocated region of memory that is independent of the number of tables or the size of the dataset. We employ several tricks to make it work without losing too much accuracy. Unfortunately, due to the time constraints, I won't be able to explain them there, but feel free to look at the implementation under the link on the slide. Now let's see how these counters are used in the context of the whole operation. Let's start with a case where the coordinator is also a replica. This happens almost always when an application uses a properly configured shard-aware driver. Because the coordinator is a replica, it has a direct access to one of the counters for the partition relevant to the operation. We let the coordinator make a decision based on that counter. If it decided to accept the operation, it increments its counter and tells other replicas to do as well. If it decided to reject, then the counter is only incremented locally and replicas are not contacted at all. Although skipping the replicas causes some undercounting, the error isn't very big in practice. On the other hand, we have saved some processing time and network resources. When the coordinator is not a replica, it doesn't have direct access to any of the counters. So we cannot let the coordinator ask a replica for a counter because it would introduce additional latency, which is unacceptable for a mechanism that is supposed to be low cost. Instead, the coordinator proceeds with sending the request to replicas and lets them decide whether to accept or reject the operation. Unfortunately, we cannot guarantee that all replicas will make the same decision. If they won't, then, well, it's not the end of the world, but some work will go to waste. However, we try to reduce the chance of that happening. First, cutting counters in half is scheduled to happen at the start of every second, according to the system clock. Scylla depends on an accurate system clock, so cutting counters on each node should be synchronized relatively well. Assuming this and that nodes accept a similar steady rate of replica work, the counter values should be close to each other most of the time. Second, the coordinator chooses a random number from range from 0 to 1 and sends it along with a request. Each replica computes the probability of rejection, which is calculated based on the counter value, and rejects if the number sent by a coordinator is below it. Because counters are supposed to be close together, replicas will usually agree on the decision. There's one important difference in measurement accuracy between reads and writes that is worth mentioning. When a write operation happens, the coordinator asks all live replicas to perform the operation. The consistency level only affects the number of replicas that the coordinator is supposed to wait for. All live replicas increment their counters for every write operation, so our current calculations are not affected. However, in the case of reads, the consistency level also affects the number of replicas that are being contacted. It can lead to the shard counters being incremented less times than in the case of writes. For example, with replication factor 3 and quorum consistency level, only 2 out of 3 replicas will be contacted for each read. So the cluster will think that the real read rate is proportionally smaller, which can lead to a higher rate of requests being accepted than the user limit allows. We found this acceptable for an overload prevention solution where it's more important to prevent the cluster performance from collapsing rather than enforcing some strict quota. Initially, after coding the solution, we found that performance wasn't as good as expected. In a local benchmark, we actually achieved an opposite effect. Rejected operations took more CPU than the successful ones. This was very strange because tracking per-partition hit counts wasn't expected to be compute intensive. It turned out that the problems was related to how ScyllaDB reports failures, namely via C++ exceptions. Exceptions are a bit notorious in the C++ community. There are many problems with their design, but they are most commonly criticized for bloating binaries with program metadata necessary for exception handling, and that the program performance when an exception is thrown can be hard to predict. Some of the projects using C++ go as far as to disable exceptions altogether due to these reasons. On the other hand, it's hard to avoid exceptions because they are thrown by the standard library and because of their interactions with other language features. Our asynchronous framework, C*, embraces exceptions and provides facilities for handling them correctly. ScyllaDB is built upon C*, so we got used to reporting failures via exceptions. They work fine, provided that errors aren't very frequent. However, during overload, this assumption is no longer true, and we notice that throwing exceptions in large volumes can introduce a performance bottleneck. This problem affects both existing errors, such as timeouts, as well as the new rate limit exception that we tried to introduce. We had some performance issues before with exceptions. In libstd C++, the standard library for GCC, throwing an exception involves acquiring a global mutex. That mutex protects some information important to the runtime that can be modified when a dynamic library is being loaded or unloaded. ScyllaDB doesn't use dynamic libraries, so we were able to disable the mutex with some clever workarounds. As an unfortunate side effect, we disabled some caching functionality that speeds up further exception throws. However, avoiding scalability bottleneck was more important to us, so it's a good trade-off. Exceptions are usually propagated up the call stack until a try-catch block is encountered. However, in programs with non-standard control flow, it sometimes makes sense to capture the exception and rethrow it elsewhere. For this purpose, std exception PTR can be used. Our C* framework is a good example of code that uses it. C* allows running concurrent, asynchronous tasks which can wait for the results of each other via objects called futures. If a task results in an exception, it is stored in a future as a std exception PTR and can be later inspected by a different task. What is nice is that C* reduces the time spent in the exception handling runtime. In most cases, C* is not interested in the exception itself, but only whether a given future contains an exception or not. Because of that, the common control flow primitives such as then, finally, etc. do not have to rethrow and inspect the exception. They just only check whether an exception is there. In addition to this, it is possible to construct an exceptional future directly, without throwing the exception. Unfortunately, the standard library doesn't make it possible to inspect an std exception PTR without rethrowing it. Because each exception has to be inspected and handled appropriately at some point, sometimes more than once, it is impossible for us to get rid of throws if we want to use exceptions and have portable code. We had to provide a cheaper way to return timeouts and rate limit exceptions, and we tried two approaches. The first approach that we explored was quite heavy-handed. It involved plowing through the code and changing all important functions to return a boost result, which is a type from the boost library that holds either a successful result or an error. We also introduced a custom container for holding exceptions that allows inspecting the exception inside it without having to throw it. This approach worked, but had numerous drawbacks. First, it required a lot of work in order to adapt the existing code. Return types had to be changed, and the boost result returned by the functions had to be explicitly checked whether they hold an exception or not. Moreover, those checks introduce a slight overhead on the happy path. We only applied this approach to the coordinator logic. The other approach that we used was to implement inspecting the value of std exception PTR ourselves. We encountered a proposal to extend the std exception PTR's interface, which included adding possibility to inspect its value without rethrowing it. The proposal includes an experimental implementation which uses standard library-specific and ABI-specific constructs to implement it for some of the major compilers. Inspired by it, we implemented a small utility function which allows to match on the exceptions type and inspect its value, and replaced a bunch of try-catch blocks with it. We got rid of throws in the most important parts of the replica logic in this way. It was much less work to do than the previous approach, as we only had to get rid of try-catch blocks and make sure that exceptions are propagated using the existing non-throwing primitives. While the solution is not portable, we use and support only a single toolchain at the time to build ScyllaDB, so it works for us. And now let's see some results. We conducted two benchmarks to show the benefits of our improvements, one for per-partition rate limiting and the other for the speedups in exception handling. Here is a benchmark that demonstrates the usefulness of per-partition rate limiting. We have set up a cluster on AWS consisting of 3 i3.4x large nodes with ScyllaDB 510 RC1. We prepopulated with small dataset which fits in memory. First, we run a uniform read workload of 80k reads per second from a C5.4x large instance. This represents the first section of the charts. Important note, the chart shows per shard measurements. Next, we start another loader instance, but instead of reading uniformly, it performs heavy queries on a single partition only, with 8 times as much concurrency and 10 times the data fetched for each read. As expected, 3 shards become overloaded. Because the benchmarking application uses fixed concurrency, it becomes bottlenecked on the overloaded shards, and its read throughput drops from 80k to just 26k requests per second. Finally, we apply a per-partition limit of 10 reads per second, and we can see that the throughput recovers. Even though the shards that were previously overloaded now coordinate many more requests per second, nearly all of the problematic requests are rejected, which is much cheaper to do than trying to actually handle them, and is still within the capabilities of the shards. Here is another benchmark that demonstrates better stability due to the optimizations on the exception handling path. A 3-node cluster similar to the previous one was subjected to a write workload to a single partition. The data included in each request is very small, so the workload is not I/O bound but rather CPU bound, and each request has a small server-side timeout of 10 milliseconds. The benchmarking application gradually increases its write rate from 50k writes to 100k writes per second, and we can observe what happens when ScyllaDB is no longer able to handle the throughput. The slide actually shows 2 runs of the same benchmark superimposed on the same charts. One for ScyllaDB 503, which handles timeouts in the old sort of way, and the other for ScyllaDB 510 RC1, which has exception handling improvements. We can see that the older version of ScyllaDB gets overwhelmed somewhere around the 60k writes per second mark. We are pushing the shard to its limit. Because we have set a short timeout, some requests will inevitably fail. Due to the fact that processing timed out requests is more costly than a regular request, the shard very quickly enters a state where all requests that it processes result in timeouts. The new version, which has better exception handling performance, is able to sustain a larger throughput. Some timeouts do occur, but they do not overwhelm the shard completely. Only at the 100k requests per second mark, timeouts start to be more prominent. And that's it. Thank you.